I suggest we get started on the second session of talks of the day. I'll be chairing the session. My name is Casper, and giving this talk is Jihee Park, who'll be telling us about semantic transformations.
Yeah. Thank you. Hello, I'm Jihee Park, and today I will present about our work, Semantic Transformation Framework for Rewriting Rules. This work is done with Jaemin and Sukyoung at KAIST. Rewriting rule-based program transformation describes program transformation as the rule which specifies to which part of the program should be replaced to each part. Because of its simplicity, it is useful for automatic verification of transformation components or synthesizing the program transformation. And the rewriting rule consists of match and substitution primitives. The match means the syntactic and semantic condition of the target component, and the substitution means the replaced component. The static analysis is mostly used to specify the semantic condition of the match part. It also defines semantics preservation property, which means the original program and transformed program is related with some formula. Because there are many frameworks with different formulation, it is difficult to analyze and compare each framework's set of expressible transformations. So, more specifically, the transformation framework has difference in the match, substitution, and semantic preservation. To specify match, some frameworks support to write the semantic condition with computation tree logic, such as logical formula with quantifiers over time and computation path information. On the other side, other frameworks can support first-order logic formula, such as with the analysis, a predefined analysis as the predicate, and also another framework can support to users make their desired data flow analysis freely. There are also differences in to specify substitution. Some frameworks support only to replace a single node in control flow graph, while others can support replacing multiple nodes in control flow graph, or more generally, the substitution in the abstract syntax tree level. There are also differences in the semantics preservation property for each framework. Some of it define it as equivalence on the notational semantics, which means the input state, when the same inputs are given, then the output states of the original program and transformed program should be equal. And some other framework can define it as a simulation relation between program states. In simulation relation, the two states are not must to be exactly equal, but it satisfies a relation which preserved after a single step over for both original and transformed program. To express the transformation uniform and systematic way, Cousot and Cousot propose a semantic transformation framework. It is a unifying framework that explains transformation and its semantics preservation property with abstract interpretation. It introduces semantic transformation to explain both syntactic transformation and semantics preservation. In this framework, syntactic transformation is considered as an over approximation of semantic transformation, and semantics preservation is considered as an equality on some abstraction of the semantics, which is called the observational abstraction. Here is the diagram of the semantics transformation framework. Given a program, first the syntactic transformation with the static analysis result transforms program to another program, and on the other side, the semantic transformation transforms the semantics of the original program to make transformed semantics. Then the semantics preservation is now, to show the semantics preservation of the concrete transformation, it is now divided into two parts. First, one should show the semantics of the transform from the program is equal to the transformed semantics of the original program. And second, they should show the observational abstraction of the original program semantics are equivalent to the transformed semantics. Although it can express general transformations, there is a still gap from the framework to concrete transformations. Although some example transformations are formulated in semantics transformation framework, but generally it does not have guidelines to prove the syntactic and semantic equivalence on the transformation. Also, the semantic transformation framework does not have mature part, which commonly exists in rewriting rule-based program transformation. So the structure of the rewriting rule-based transformation and semantic transformation is different. So it is hard to correspond the component of the semantic rewriting rule to semantic transformation framework. To solve this issue, we define a semantic transformation framework tailored to rewriting rules, and we provide syntax-directed guidelines to prove syntactic semantic equivalence. And also, we further present theorems that simplify proofs by identifying properties of transformation, and we define 6 well-known program transformations to show feasibility of our work. First, I will show how our semantic transformation frameworks are defined and how we provide the syntax-directed guidelines. The target transformation of our framework is the rewriting rule-based program transformation, which have match and substitute primitives. And also, our target transformation is based on semantic transformation, which means the transformed program's semantic, which is execution trace, should depend on only original program's execution trace and the program analysis result. So, if we think about the transformation which replaces arbitrary expression to arbitrary value without any analysis, it is not in our interest because the transformed program's execution trace is not dependent on original program's execution trace. It is just arbitrary. To show our work, so we define a target language. It is just a simple imperative language with while and loop and branch statement, and it has just the integer and boolean values. We define the semantics of the program as the trace semantics. This is the example program, and the trace of the given program is given as follows. The trace is an ordered collection of the information, ordered collection of the events during the execution of the program. More specifically, trace is defined as the sequence of program label and the action. Action means the action describes what effect on the program what effect on the execution of the statement and how the execution of statement affect to overall program. So, for example, when the program executes the statement, assignment statement, then the action records assignment action, which consists of assigned variable and the expression, which is in the assignment expression, and the evaluation of the expression on that execution. Similarly, when the program executes the branch or loop condition, then it records the evaluation of the condition. Now we show high-level overview of our approach. It consists of 4 parts: matcher, syntactic substitutor, semantic substitutor, and the correctness argument. The matcher matches program with target statement and whole program static analysis result. And it produces output which is needed to syntactic and semantic substitutors. Now we will show our components with the example transformation, the constant propagation transformation. So the matcher needs a program component and the analysis result. For constant propagation transformation, the required analysis is value analysis of each variable. So the analysis returns the possible values at the label. And the matcher or constant propagation matches the statement when the target statement is the assignment expression or assignment statement of the variable expression, and the target variable has only constant possible value. Then it returns the triple, consists of the matched label and assigned variable and the constant value. So in this example, the matcher matches the label A to produce a triple. A consists of 8, Y, and 2. And after the matcher matches the target component, the syntactic substitutor specifies how to replace the match statement. It generates transformed statement from match statement and matcher output. So for our example, the syntactic substitutor is using the matcher output to produce assignment statement of constant expression. So in this case, the matcher matches to label A and produces Y assigned to 2. Note that the original program and transformed program is different only for the matched part, and other parts remain same. And semantic substitutor, on the other side, semantic substitutor specifies the effect on program trace. Regardless of the syntax, it generates transformed trace from the program trace of original program and the matcher output. The semantic substitutor for constant propagation is defined as follows. It replaces only for action which passes the matched label, and it changes the action of the matched label into only for the expression part. It changes the expression part to constant expression. So when the original traces have the action of some unknown expression, then it replaces the expression to the constant expression. So in the constant propagation transformation, the semantic substitution only changes the action of the matched label, but for more complicated transformation, the semantic substitutor can also delete or insert new actions in the trace. After defining matcher, syntactic, and semantic substitutor, we should show how the syntactic transformation and semantic transformation are equivalent. So we call it as correctness argument, and it states that semantics of transformed program is equal to transformed semantics of original program only when the matcher produces a valid matcher output. So this equivalent is up to the matcher output. We proposed the syntax-directed proof for rewriting rule-based transformation, which is the main difference of previous semantic transformation framework and ours. We divide the correctness argument into two parts. First is base case, and second is inductive case. The base case carries proof for the equivalence for only the matched part, and it ignores the surrounding part of syntax. On the other side, the inductive case provides the proof for surrounding part of the syntax. So I will show the correctness argument with the examples. First, the base case relates syntactic and semantic transformation when the whole program is matched. So in this example, the original program y assigned to x and transformed program y assigned to 2 is equivalent up to the matcher output 8, y, and 2. To more specific, the definition of correctness argument is defined as follows. When the original program is transformed with syntactic substitution with the matcher output, then it produces transformed program. And for a trace which have the original program trace as a subpart, then it is transformed with semantic substitution with the matcher output. Note that the important thing is that the original trace have the trace should satisfy the matcher output. It means in this case, the value of x at the end of T1 should be 2 to satisfy the matcher output. In this restriction, the correctness argument is the proof of the equivalence between the transformed trace and the transformed programmed trace. So after the base case, the inductive case proved the correctness argument for the component surrounded by context. Context means the statement with whole, which will be filled with two components, which will satisfy correctness argument. So in our language, there are 5 kinds of whole. So we should show the inductive case for all 5 cases. Suppose we prove base case and inductive case for all contexts for constant propagation transformation, then I will show how the correctness argument of arbitrary program is proved. So first, the base case carries proof only for matched part, and after using induction for the sequence statement, then the correctness argument is propagated to a larger program component. And next, using induction again for branch context, then the correctness argument is propagated to a more larger program component. And after repeatedly applying this induction for appropriate context, we can prove the correctness argument for any two program which is the result of the syntactic substitution. The advantage of the separation of base case and inductive case is that for base case, we just consider the matched part, and we can ignore the surrounding part with the assumption of the valid matcher output of trace. And in contrast, for inductive case, we can ignore the inner component of the syntax, and just we can use the fact that inner components are related by correctness argument. So we exploit this fact to reduce more burden of users of proving inductive case. I will show it later. And yes. So we provide the syntax-directed guidelines to prove, but there is still a burden to user to prove correctness argument for base case and all inductive cases. So we present theorems that simplify proofs by identifying properties of transformation, and we define 6 well-known program transformations to show feasibility of our work. So there are some example properties of semantic substitutor. First is concatenation preservation, which means the substitution of 2 concatenated traces is equal to concatenation of substituted traces. And second, control flow preservation means that substitution of branch, loop, or sequence section is preserved. And next, final state preservation means that for any trace, the value of the variables in the end of the trace is equal to value of variables in the substituted trace. Using the properties of these kind of analysis, syntactic and semantic substitutor, we introduce theorems to prove induction for some contexts. For example, when the semantic substitutor satisfies concatenation, control flow, and final state preservation, we have free induction cases for loop context. Similar to this, we introduce 5 theorems which require some properties of the component of transformation. More details are in the paper. And we define to show the feasibility of our work, we should define the transformation component of 6 well-known program transformations and define and prove the correctness argument for these 6 kinds of transformation. For all 6 transformation, we define the base case manually. We prove the base case manually, but for inductive case, we just prove it manually for only data assignment elimination transformation. And for all other 5 transformation, we use the properties of the transformation to show the inductive case to eliminate to show inductive case using theorems. So to summarize, we propose a semantic transformation framework, which is tailored to rewriting rule, and we show syntax-directed correctness argument to show to provide a guideline to prove correctness argument. And to further reduce the burden of the user, we introduce the theorems to reduce the theorems to show inductive cases for some context, and we define 6 example transformations in our framework to show feasibility of our work. Thank you for listening and welcome question.
Thank you for an intriguing talk. So, in the compiler verification literature, there has been some attempts to verify the compiler correctness using some compositional concept of simulation relations. So, would you please compare this somehow modular or compositional simulation approaches to your approach?
Thank you for a great question. Simulation relation, the difference of the simulation relation and ours is that in simulation relation, the states should be matched exactly, but in our semantic transformation framework, the exact correspondence or preserved after fixed step of time, our trace does not have this kind of strict regulation of the correspondence. We just need to define which trace will be replaced to which path, which trace, and I think it is the more general to simulation relation. And there is also similarity with the simulation relation and ours, because the simulation relation also satisfies the original state, correspond original state to transformed state, and our semantic transformation framework has original trace to place the transformed trace. Thank you. Yes.
So you proved you implemented 6 different program transformations. Were any of those transformations the same as Cousot's? I mean, you're taking the framework of Cousot and Cousot and you're making it easier, better. Is there any? Could you give any sense of what is the differences in what you did, and did you apply to similar examples? And can you compare the proofs and the transformations, or were it different languages?
Thank you for question. I think in Cousot's paper there are 2 example transformations. First is constant propagation, and second is monitoring the traces in something. And I think the main difference of Cousot's framework and ours is that we use the mature part to identify which part should be replaced to effectively reduce the core part of the proof. So it is considered as base case. And for inductive case, I think it is not a core part of the proof. So it is better to eliminate it using the common properties of the transformation. But I think in Cousot's framework, Cousot's framework can work for not effectively work for rewriting rule-based transformation. I think that.
Could we go back? Or actually, it's on the slide here, but you have this list of theorems that you say that you prove. What's the reason why you divide into action-wise and not action-wise? It seems to me that one should be stronger than the other, but maybe this is not true. So what? So you did it for a reason. I'm curious.
Action-wise, semantic substitution is semantic substitution which works for every action. It is something like a map function, and non-action-wise is the semantic substitution which does not work as map function. And for action-wise transformation, it is more easier to prove the elimination of induction case, but while proving the same induction cases for non-action-wise semantic substitution, and I failed to prove it because of the I don't know why I failed it, but with the more assumption with matcher and semantic substitutor, we can prove it also for non-action-wise transformation. So the result is same, but the precondition is different. The action-wise semantic substitutor can prove theorems with only properties of semantic substitutor, but for other theorems, it requires a property of syntactic substitutor and matcher analysis. So I think it's different.
So I'm asking, I'd like to ask about the power of this framework. I believe that this framework is complete for the transformations based on value analysis. Is it correct?
For what?
I mean, if transformation is explainable with value analysis, probably you can prove that in this framework.
Value analysis. I think it is more general than only value analysis. In our example, we use Leibniz of the variables to show the equivalence, correctness argument of elimination, that assignment elimination. So I think it is not explainable with only value analysis.
I see. Does it scale to more advanced optimizations like the no alias information or some alias analysis, these things?
I believe that we can prove it for the sophisticated analysis, but we do not actually prove